Presenting our work, Topology-Aware Knowledge Propagation and Decentralized Learning. Machine learning dataset sizes are growing, and so it really asks the question, how do we learn efficiently? And there's only one answer. We need to divide and conquer. We must distribute our training over all available compute. How do we coordinate distributed learning? Well, simple algorithm. You first divide your data across workers. Each worker trains locally, and then periodically, each worker is going to coordinate via some central coordination to average its gradients with all of the other workers in the training run. So when this algorithm is implemented within a data center setting, we call it data parallelism. In this geographically centralized setting, there's two main drawbacks. One, data privacy concerns. If this data wasn't generated at the data center, it's likely moving from somewhere, perhaps a hospital. People may or may not be hesitant to share this data. And two, data transfer costs. Again, in the scenario where you're moving the data from generation site to compute site, you may incur a hefty communication cost, especially since ML dataset sizes are growing. To alleviate these concerns, we now have the option to do this exact same algorithm, but via local compute. This is called federated learning. So what's happening here is that we're moving the compute to the data generation site, alleviating privacy concern and data transfer cost, but we are still coordinating communication between these workers via some central server. A concern here is the susceptibility for single point failure at the central server. If that server were to go down, none of these local compute sites could communicate with one another and benefit from each other. And two, that central server, depending on where it's located, may unfairly penalize compute sites which are further away or for some reason have worse networks, higher bandwidths. And so to alleviate this, what we really need from a systems design perspective is learning without centralization. What do I mean by this? Well, it's a very similar diagram to the previous screen, but the thing that's missing is that central coordination server. Instead, what we have are connections directly between local compute workers. And what these connections enable are communication channels. And so how do we learn? What's the algorithm in this setting? Very similar to before. You divide the data across workers. Each worker trains locally. But the key difference here is that every single time a worker wants to aggregate with other models, it must do so within its neighborhood. So let's say that the worker we're interested in on the screen highlighted in yellow wants to receive new information and communicate what it's learned. It's going to go and query its neighbors, indicated in yellow dots. You know it's a neighbor if it's connected via a direct communication channel. And it's going to do an aggregation step or an average within that setting. And we're going to redo this aggregation for every single word in the topology. And so what does this very simple algorithm enable us to do? Well, suddenly we can coordinate learning in these really arbitrary, complex communication topologies. We're not too worried about fault tolerance. If any one of these nodes go down, it doesn't affect the other nodes nearly as much. And we can even accommodate dynamic moving nodes in a topology as well. So practically, how does this algorithm fare in terms of learning performance? Well, on the screen, we have a result where we are distributed MNIST across 33 different nodes in a topology. Each circle represents a node and each line represents a communication channel. And what I have mapped via the green color is the accuracy of MNIST at each node over the course of training. And what I hope is visible is that that dark green, which indicates high accuracy, is increasing over the course of training. What I omitted here is the fact that this data was distributed very independently and identically, meaning each node had very similar data distributions to one another. What I also did is that in addition to this identically distributed data, I had also dropped some OOD data or out of distribution data on a single node within topology, node 6. And we trained concurrently, but what we did is we tracked the accuracies separately. So what we're seeing in the bottom row is the accuracy of that OOD data over the course of training. And while we see that the OOD data accuracy is indeed increasing and spreading, it's not to the same extent as the IID data above it. So what can we do to resolve this difference in performance? We propose topology-aware aggregation, a very simple algorithm that can be added to any decentralized learning scheme, but which makes use of a node's location information within the topology to decide how to weight it at aggregation time. So the experiment we showed before was done using scenario A for aggregation. In this scenario, the aggregating node weights all of its neighbors equally. What this scenario does is it fails to account for whether a node is well located or badly located within a topology. And what scenarios B and C do is it makes use of this information. So in scenario B, what we weight nodes by, or what we suggest weighting nodes by, is by their degree, or how many neighbors they have. The hypothesis here is that a node which has a lot of neighbors may be in a really good position to both receive tons of information and also communicate it. In scenario C, the metric that we suggest using is called betweenness. Betweenness is interesting, and what it weights a node by is how well placed that node is within a topology to connect communities. So under the hypothesis that different communities have different types of data, perhaps OD to one another, the betweenness nodes, the highly weighted betweenness nodes, could potentially bridge those communities and allow data to flow faster. And so we see that topology-aware learning actually does accelerate knowledge propagation substantially. So in scenario A, that's the experiment. You see that ID data is propagating really nicely, indicated by the dark green, but OD data is not quite there yet. It needs to catch up. It's not propagating fast. What we see in scenario B, in a topology-aware metric, degree or how many neighbors in have to weight it respectively. ID data propagating well. Now exciting, we've doubled the propagation of OD data in the same amount of compute. And so this is parcel fest, so I want to touch on the role of parcel in our work. What we needed was a way to simulate learning for a vast number of under a vast number of data distributions. And we use parcel to do this fold. First, we use parcel to parallelize the training of independent nodes within a topology prior to aggregation. And we also use parcel as a second wrapper to parallelize at the experiment level. And with that, I'm going to wrap up. I'm happy to take questions. Here's a link to a blog which has both the code and a short write-up to the paper. Thank you.